Hi there. In this video, we're going to keep going in Chapter 10, and we're going to look at polar coordinates. Many of you have seen this before in a pre-calc or trig class. It's basically the same stuff, not a real long section, and you don't have to graph any of the curves by hand, so we're going to use a calculator for that. So that should make this easier than your previous class where you saw this stuff, I would guess. So just some terminology. Make sure you're familiar with the terminology. The pole is just any point in the plane, and we label it O. And then you can draw, so it's called a ray, it's a half line, and it's called the polar axis, and we just go out to the right. So this is like the positive, it's like the bottom boundary of the first quadrant. P is any other point in the plane. R is the distance, so R stands for radius here because it's polar, so we're imagining circles. And it's the distance from O to P. And theta is the angle in between. And we always measure counterclockwise as positive theta. Same as your trigonometry version of this stuff. And then the coordinates are R and theta. So R tells you how far to go from O. Theta tells you how far to go counterclockwise. And those are polar coordinates. And we can extend polar coordinates to go negative R as well. So here's R theta. And if you do theta plus pi, that's 180 degrees away. If we took R to here, it would be the same distance. But if we take negative R, it becomes the same point. So that's the idea, right? So taking a negative radius with the same angle is the same as taking the positive radius with theta plus pi. Right, so negative r theta and r theta plus pi are the same point. Now you could do theta minus pi. It's the same thing, right? Going clockwise is the same thing. And then there's a convention we follow that if the radius is 0, then theta is what's called a free variable, meaning that the angle doesn't matter if the radius is 0. It's just the pole. All right, so we're going to do a little bit of work with this. We don't spend a ton of time on this stuff, but you should have some familiarity. So we want to find a positive radius and a negative radius that has the same coordinates as this point. Well, this one already has a positive radius, so we're going to leave that alone. So let's find another one with the same radius. And so you just add or subtract 2 pi, right? So in this case, I just subtracted 2 pi. It doesn't matter, though, if you add or subtract. And now we want to find a version of this with a negative radius. So if you make this negative, we have to add pi to this, or subtract pi, but we're going to add pi. So you switch the radius, and then this becomes that plus pi. So negative pi over 4 plus pi is 3 pi over 4. And then plot the point. So the idea here is the radius is 4, so we go out 4 units, and then you go around 7 pi over 4 times. Well, that's almost 8 pi over 4, so you go all the way around and end up here. But it's easier to think of it this way if you want to graph this one instead. Go 4 and then come back, go negative pi over 4, takes you to that point. Again, you're not going to have to graph this stuff by hand, but you should have a decent understanding of it. All right, here's another point. This one is given to us with a negative radius, but a positive angle. So keep the radius the same, add or subtract 2 pi. So I added 2 pi. And then flip the sign on the radius, and I subtracted pi. And so, you can graph, all 3 of these are the same point, but if you want to think of this one down here as the positive radius, right? So you go out 5 units, and then you come around 7 pi over 6. So there's 6 pi over 6, 7 pi over 6 takes you there. Pretty easy stuff. Now, sometimes we need to convert from polar coordinates to regular coordinates. So if you're in rectangular coordinates and you want to go to polar, just plug in x and y. So x squared plus y squared is r squared, right? This is Pythagorean theorem, but it's also the equation of a circle. And to find the angle, it's just tangent of theta is y over x. This is not quite the same as arctan theta. I'm sorry, as arctan y over x is theta. It's not quite the same because we're allowed to pick any point from 0 to 2 pi. So you just want to think about either the unit circle or reference angles when you're doing this stuff. And we'll see an example of this in a sec. To go from polar to rectangular, just use these two formulas. These are just, again, the definitions from trigonometry that involve right triangles. And last one, when you need to find the distance between points, you're basically just taking the square root of this, and it just turns into the distance formula, right? So this is just the distance formula. Okay, so let's convert both of these to rectangular coordinates. So pretty easy stuff. So first off, x is r cosine theta. There's cosine theta. Convert it. Make sure that all your answers are exact values if possible, so no decimals here. Same thing with y. It's just r sine theta. Plug everything in. Make sure you're in the right quadrant when you do this stuff, right? Make sure you know your reference angles when things are positive and negative. All right, for the other one, pretty similar, right? Just plug everything in and do it again for the y coordinate. And if you go back, so these are the same 2 points from example 1. If you go back and look at the coordinates, you can see that the rectangular version is the same as the polar version. So they plot the same points. All right, not real super exciting, but again, make sure you know how to do this stuff. All right, so now this is a slightly different type of problem. This is a polar inequality where we have to shade regions on the graph. So what we want to do is use the other translation formulas that we saw, right? R squared is x squared plus y squared, and tangent of theta is y over x. So we're going to use those to do this. So look at what this is saying, right? This is saying that the radius of the circle is somewhere between 3 and 4, right? So R is just in between these circles. So if we were to like just draw 2 circles, we would shade like the ring area in between these 2 radiuses. This one here is saying that the angles on theta are between 5 pi over 3 and 7 pi over 3. So we have to find where these angles are. And again, you know, it would be every point along the lines determined by tangent of these angles. Right? So you just plug the angles in. Remember, the equation is tangent theta is y over x. I just multiplied both sides by x to get a function. So these are both functions. In terms of y in terms of x. These are functions in polar, but I know how to graph circles. And so I just graphed all these circles and lines. Right, so here, this is positive radius, 5 pi over 3. Here's positive radius, 7 pi over 3. And obviously the 2 circles. So now we just have to figure out where the inequality is. So if you go back and look, r is between these, theta is between these. So that's real easy. So it's going to be in this ring, and then it's in between the angles. When you write it like this, we're assuming that r is positive. Notice r is given that it's positive, so it's going to be on this side where the radius is positive, because here's 5 pi over 3, and here's 7 pi over 3. So it's in between these 2 lines and in between the rings, so it's right there. Notice that the inequalities for the radius were strict inequalities, so you have a dotted line here. the inequalities in between the angles, included the boundaries, so you do solid lines. So there's your region. Now what we want to do is find a way to rewrite polar curves as Cartesian curves. It's really easy to go the other way. You just use x equals r cosine theta and y equals r sine theta. So translating from polar to rectangular is really easy when you're given the rectangular polar is easy. Here, we want to go the other way. We want to write this as x as a function of y, if we can, or y as a function of x. So it takes a little bit more work when it's not in a nice format. So the trick with these usually is our formula that involves r squared. So a good trick is usually just multiply through by r, because we need an r squared over here. So I multiply both sides by r, and I just rewrote secant and tangent as sine and cosine. Our other equations for translating between polar and rectangular involve sine and cosine. So let's get these in terms of sines and cosines. Now what I did is I divided both sides by r squared. I know that might seem weird because I just multiplied through by r, but I'm trying to move stuff around where I need it. My formula for x and y, I need an r sine theta, I need an r cosine theta, I need an r sine theta. So this on the left is going to be 1. This is going to be y, x, x, right? Now I have a function involving only x's and y's. Multiply them together, solve, and you get a parabola. So it turns out that r equals tangent theta secant theta is really just y equals x squared. So that's a surprising connection between these functions. So here are some common polar curves. And just remember that when we define graphs of polar curves, it's similar to how we did it with rectangular curves. It's the set of all points P that have at least one polar representation whose coordinates satisfy the equation. There could be multiples of these, right? Because polar curves can do lots of weird stuff. They can self-intersect and things like that. So we're just saying at least one polar representation. Maybe you won't be able to find it, but it exists. So here's a couple common ones that I found. If you have r equals k squared, that's a circle centered at 0, 0 with radius k. If you have r equals 2k sine theta, that's a circle at 0k with radius k. 2k cosine theta, circle at k0 radius k. Remember this, if this is negative, the center is moved, but a negative radius is still a circle. Theta equals c. That's the line y equals tangent c of x. We saw that when we did the graph problem a second ago. And we just saw this. Right? This is a parabola, vertex at 0, 0. Turns out there's another one. The way you get the hyperbola, centered at 0, 0, it's r squared cosine 2 theta equals 1. So this is a real kind of strange looking equation. Now here's some more graphs of just things you might see. You don't have to memorize this stuff. We're going to be doing all graphing work on a graphing calculator, so you don't have to do anything too fancy. But this is in the notes. You can look at it. And again, you can graph it on a graphing calculator. So that's just a few of the things that we can see. So what we want to do here is graph this. Now, we're not graphing by hand. We're going to do this on the graphing calculator, so get your calculators out. And we're doing this like we did the parametric equations, right? You go to mode, scroll down to pole. Click y equals, type in sine 2 theta. Go to your window, enter the range given for theta. For this problem, theta is not given. If theta is not given, you really don't know what to type in. So I just did 0 to 2 pi. The only time you can make a mistake with theta max is if it's not big enough. So if your graph doesn't look complete, make theta max bigger. Put in 4 pi or 6 pi or something. Then you can go to zoom, go down to zoom fit, and it fits it real nice, and you get this. So the reason that we're talking about graphing polar equations is the same as what we did when we did parametric equations. We want to know where this curve intersects itself. So r equals sine 2 theta here. You can see there are 4 intersections, right? It starts at the pole, 1, 2, 3, and then ends again, 4, right? And the reason we need to know that is you might be asked in the next section, say, to find the area of one of these. Well, when you do the integral, you have to know that you're only going 0 to pi over 2. Because if you do 0 to 2 pi, you're going to find all 4 of these areas. So we have to know where these intersections are, right? So another trick you can use is you can change the theta range. If you think that the graph only goes 0 to pi over 2, then just type in 0 to pi over 2. If it only draws one of those loops, then you know when you do the integral what to set for your limits of integration. So make sure that you guys, on the homework, I don't care if you use a calculator to graph those things or not. Some of them have like A's, B's, and C's in them and K's. So those you kind of have to either do by hand or use this list or this list. But most of the time you can just put a number in there and you can see what happens. All right, well, that's it for this video. If you have any questions, let me know. And I'll see you next time when we do calculus with polar coordinates. All right, bye-bye.